Let's turn our attention to instrumentation. There are many different types of variables that need to be measured and controlled, and we'll go through the various technologies and different variables and how they might be measured and controlled. One of the most important variables to control is temperature. If you think about your car, if you take it to the North Pole, it probably won't start, right? Because it's too cold. Your car is designed to operate in a certain temperature range. Your body works only in a certain temperature range. There are many things, even industrial processes, of course, that temperature has to be right for the process to go as desired and planned. Thermocouples are a really cheap way of measuring temperature. At least the sensor itself is inexpensive. If you look at the upper right figure, you'll notice a chromel and alumel wire touching together. And what this represents is two dissimilar metals of the type shown there. Those are two separate alloys that are together. Now look at the lower figure and you see that there are two junctions made here with an iron wire and a copper wire. Now the place where the flame is impinging on the junction on the left, that is the sensing junction. And the junction on the right-hand side is what's called the reference junction. And if you actually set this up as an experiment, it turns out that if you put an ammeter in line with the copper wire or with the iron wire, you could measure current flow. Now the amount of electric potential in volts that are generated because of the difference in temperature between the flame end and the reference end, that amount of current and voltage would be pretty small. But it can be measured, and it turns out that the voltage is pretty much proportional to, or dependent on, the difference in the temperature between the 2 points. Now, for practical purposes, we don't typically just have two dissimilar wires that are connected to either end. Rather, we connect the thermocouple, which is the two dissimilar wires, we connect them at one end, at the sense end, you see that in the pink box on the left in the upper figure, and then connect it to sensing equipment, which will have its own types of wires. For example, copper. Copper is a fairly common wire. Now, since there's a dissimilar metal between the chromel and copper junction and a dissimilar metal between the alumel and copper connection, those junctions also generate their own millivolt signals. So in order to cancel the effect of those junctions, what you have to do is know the temperature at those junctions, and then if you know what types of materials are there, and you know the nature of those which has already been measured for you, then you can cancel out the effect of the reference temperature and back calculate the sense temperature. Now, the expensive part of a thermocouple is not the wire itself. The wire is relatively cheap, from pennies to at most dollars or so per foot. The expensive part is everything from the reference junction back, because you have to have some other method for measuring the temperature at the reference junction, and of course you have to have the associated electronics in the meter in order to calculate the sensed temperature. On the left you'll see a typical industrial thermocouple. You notice that the place where it plugs in is that yellow plastic housing. One interesting thing about these, they typically have the same type of material for the blades that the wire is made from. So if this is what's known as a type K thermocouple, that's a chromel alumel wire set, then the blades there will be made out of the same materials. Now you'll notice, I don't know if you can tell from the picture, but typically one blade will be a little bit wider than the other, and the reason for that is so you can't plug it in backwards. Now, thermocouples have very wide temperature sensing ranges. Many thermocouples can withstand flame temperatures. These are just metals, and as long as the metals don't melt and don't go too far out of range, the metal can sense very high temperatures. Now, there is a trade-off. Thermocouples aren't known for their accuracy. They're fairly repeatable, but they're not all that accurate, and so calibrating them is very important if you want to get reasonable results from them. Now, the end of the thermocouple sometimes is shielded, and so we see on the left-hand side of the 5 figures there's a sealed sheath covering the thermocouple. Now, one of the problems with the sheath is that it adds a lot of thermal mass, and so it takes longer for the junction to come up to the temperature to measure the temperature of, say, a flame or whatever, maybe a liquid that it's inserted into. A sealed sheath, while it protects the thermocouple, does increase the response time. So it takes longer for the thermocouple to respond to changes in temperature. There is a cutaway for the next image that is showing a sealed thermocouple that is also isolated from the sheath. So you'd want some type of material filling in there in order to transfer thermal energy from the sheath to the thermocouple, but electrically they would be isolated from one another because often you don't want the thermocouple wire, which is part of an electrical circuit, to be grounded. It's very common that the sheath itself is made of metal and is grounded. So this further degrades the time performance, or the amount of time that it takes for the thermocouple to respond. If you need something to protect the thermocouple from the environment, but it's okay for that junction to be grounded, then you can use the middle option, which is where the thermocouple is sealed and grounded to the sheath. Now this will have improved performance in terms of responsiveness to changing temperatures around the sheath. Now another option is the exposed fast response type. Now this type, of course, just leaves the junction exposed but protects the wire leading up to it. And then there's the option of an exposed bead. Now, it's common to use a thermocouple welder, which is usually just a small thing. It's not like a welder like you'd use for stick or MIG welding, but it's just a small welder where you put the two wires in, usually a desktop unit. It generates a high voltage, and a very small bead melts together of the two materials, and that's the sensing junction. And typically you want that bead to be small so that it has very good response characteristics, and it doesn't take forever to heat up a glob of weld, and so your thermocouple responds rapidly. Grounding is not always a consideration. If you have a handheld meter like this rather than installed equipment, it's fairly common to get a meter that can measure temperature. Some meters are made just for measuring temperatures, and usually multiple temperatures. And so you see a Type K thermocouple, which is by far the most common, connected to this multimeter. And temperature measurement is one of the functions that multimeter offers. There are many different types of dissimilar metals that can be put together and form a junction in order to measure temperature. Type K, as I said, is the most common. It has a nice wide temperature range, reasonably accurate, although it's not perfect, of course. But other types of thermocouple materials or thermocouples have their own letter assigned to them, and they have advantages and disadvantages in terms of their accuracy and their applicability and compatibility with a local environment. On the other end of the spectrum are resistance thermal devices. These are very expensive, or relatively expensive, temperature measurement devices. Typically, the way these things work is they're essentially a resistor that depends on the temperature it's exposed to. And so the resistance element itself is usually made of platinum. That's part of what makes these devices so expensive. And they're most often covered with a sheath in order to protect them. So you see a picture of one there on the right. And they're much more expensive, but also more precise than a thermocouple. Now, typically a resistance thermal device cannot measure as wide a temperature range as a thermocouple. There are also thermistors. Now, these are commonly used for sensing reference junction temperatures. They are nonlinear in the sense that their resistance does not vary linearly with temperature like an RTD does. But as long as you can calibrate it and keep a calibration curve, then you can measure the resistance of the device and back calculate the temperature. There are many other types as well. There are many different semiconductor types. But let's move on to another variable, mass flow. Measuring mass flow is very important in many processes. If you think about a turbine used for generating electrical power, the turbine will have steam flowing into it, and measuring the mass flow rate of that steam is critical to control the process. The air flowing into the engine of your car needs to be measured, and so there are mass airflow sensors, and we'll talk a little bit later about how those work. Now, one way to measure the mass flow through a pipe or a venturi, such as is shown here, is to measure several different properties, such as the density of the fluid, the velocity of flow, and the cross-sectional area of flow. But there's going to be mistakes or inaccuracies in all of these measurements, and so once you multiply them all together, the error is compounded. And of course, we're using a continuity equation here to calculate the mass flow rate, but we're really not measuring the mass flow rate directly. There are meters for measuring, or sensing devices, for measuring mass flow rate directly, and they work on at least this type, the Coriolis type, works on the principle of inertia. So as a stream is flowing, it has mass and therefore has inertia and doesn't want to change its direction. And so the pipes that you see here, these tubes, these bent tubes, are oscillated on purpose back and forth. The fluid resists that oscillation and causes oscillation in other areas of the pipe. When you measure that other oscillation, that resultant oscillation, and look at the phase difference between the exciter and the responder, you can actually calibrate and figure out the mass flow rate. There's a nice video linked here, and I'll link it elsewhere to explain how this device works in a little more detail. There are also flow rate sensors for, rather than measuring mass flow rate, measuring volume flow rate. And they usually work on the principle of actually measuring a principal difference. So if we look at the different types of flow restriction devices there, you see a Venturi tube. And a Venturi tube obviously necks down to a smaller flow area and then expands back out. Now, when the cross-sectional area is reduced, the pressure in that area goes down, and by measuring the pressure difference before and at the throat, that difference in pressure, you can figure out the flow rate. It turns out that the flow rate Q, the volumetric flow rate, is proportional to the square root of the pressure difference between those 2 points. This is not a fluids class, so I'll not go into why that is, but it's simply the case. Now, you don't have to use a Venturi to cause a flow restriction. Another option is to use an orifice plate. An orifice plate is simply a plate inserted into the flow stream that has a hole in it. And there's many different sizes and geometries of flow passages in the orifice plate that can be switched out at will. And this is a nice feature. You know, if you have a need to measure flow rate in one region or one range of flows, one day put in the right orifice plate. The next day, if you need to measure a higher flow rate, put in a different orifice plate. So it's a flexible device. However, the Venturi tube has nice pressure recovery. In other words, the pressure at the entrance to the tube is at whatever level it's at, and then it goes down in the throat of the Venturi, but then it recovers and comes back almost to where it was before if the Venturi is designed right. In an orifice plate, usually the pressure recovery is very small, so there's not a whole lot of pressure recovery. Rather, there's a lot of pressure loss, and that's a permanent change. What that translates to is needing more pumping power to keep the flow going. But flow nozzles are sort of like a mixture between a Venturi and an orifice plate. They're not as expensive as a Venturi tube. They're also more flexible. A lot of times you can take a flow nozzle and change it out to a different nozzle. And because of the rounded inlet, there's less pressure loss. There's not as much pressure recovery typically as in a Venturi tube, but then the cost is typically somewhere between a Venturi tube and a simple orifice plate device. But the principle in all of these is the same, and that is that you cause a pressure change, and from that pressure change you can calibrate and figure out the flow rate Q. And now this is a volume flow rate, understand, not a mass flow rate. If you've ever looked at a small aircraft, you've probably noticed pitot tubes on the wing, though you may not have known what they were. They're small pipes coming down off the wing and typically facing forward. Well, in fact, as far as I know, they always face forward. And basically what these devices do is measure the difference between what's called static pressure and dynamic pressure. Again, this is not a fluids class. I won't go into the details of how this works, but because of that pressure difference, you can figure out the velocity of the airstream going past it. And it just has to do with an energy balance and the fact that the kinetic energy is transformed into pressure, if you want to think of it that way. Okay. There are other types of flow devices where the flow rate is proportional to the angular speed. For example, there are paddle wheel sensors. If you look at this, the way it works is the paddle wheel rotates around, and each one of the different sections passes a metered volume of fluid. So if you measure the rotation rate or you measure how many of the blades have gone by per time, you can figure out how many volumes of fluid have passed this point per time and measure the flow rate that way. There are many other types of flow rate sensors, and I'm going to have you watch videos. Each one of these are links, but I'll link to them separately. Whichever way accessing them is easiest for you is fine with me. But each one of these different methods has its own region of use. None of these are flow meters that are used for every single situation. It depends on how fast the flow is going by. It depends on what is flowing by, what it's made of. For example, the electromagnetic flow rate measurement sensor has to have a liner that is non-conductive, and the fluid flowing through it has to be conductive. I'll let you watch the video to see why that is, but Obviously, this won't work for a non-conductive fluid like, say, gasoline or something. I mentioned your car's mass airflow sensor. Another way to measure flow rate is by heating up a resistance so that the temperature of it goes up, and then controlling the current going to that resistor so that you maintain the temperature constant. See, as air flows by, for example, it will cool the resistor, and so the temperature will tend to drop. So you have to pump more current into the resistance element in order to bring the temperature back up to the set point. And so by measuring the amount of current required to maintain the temperature of the resistance element, that can help you calculate or back calculate the air flow rate. Another common method here is, rather than holding the temperature constant, rather just put constant current into the resistance element and measure the resulting temperature. Again, this can be calibrated to give you the air flow rate going past the sensor. And I don't remember which way cars typically work. It's one or the other. Another way is with something called a flow target in the lower right-hand image. You've probably done something like this. If you ever stuck your hand out of your car window as you're moving, you notice that at higher velocities, the air pushes your hand back farther. That's exactly how this works. You see the target down there is in the flow stream, and the flow pushes on this target, and the target is essentially spring-loaded, so that the higher the flow rate, the harder the flow pushes against the target, deflecting the target farther and farther against the spring, and by measuring that deflection, you can infer the flow rate. Other types of sensing technologies use sound. So the first type here on the left is a transit time type, where there are detectors and receivers at both ends of the pipe. So at the lower end there's a transmitter, and at the upper end there's also a transmitter. Both send a sound pulse and measure the amount of time it takes for that sound pulse to go across. When there is no flow, of course the amount of time required is the same, but when there is flow, one transmits faster than the other. And again, I'll let you watch the video to see more detail of that. If you've ever sat at a railroad crossing and heard a train go by as it blew its horn, you've noticed that the frequency of that horn decreases, right? As it comes toward you, it's actually higher than reality, or with reference to the train, and as it goes past, it's lower. And the reason for that is because of the motion of the train itself. Well, that idea is being used in the Doppler type flow rate sensor, where a transmitted pulse is sent out, reflected off of particles in the flow, and received by a receiver. Now, because the particles are moving, they will change the frequency of the sound, and that shift in frequency can be detected so that the particle speed can be inferred, and therefore the flow rate inferred. Fluids are not the only type of flow that you would want to measure. There's also solids flow. What if you have a conveyor that's taking coal up to a coal-fired power plant, or gravel from a rock crusher to be put into a pile? How would you measure that flow rate? One way to do it is by supporting a section of the conveyor with just a weight sensing scale, essentially. And if you know the amount of weight on that segment of the conveyor, and you know the speed of the conveyor, then you can figure out the flow rate of solids. Now, flow rates are not the only things to be measured. Level is another thing. This is a bubbler level type of measurement device. If you think about a volatile or explosive or flammable fuel, you probably don't want electronics near it that could possibly ignite a fire. You want the electronics for measuring the level in the tank to be remotely located to the tank, where you can ensure that they won't spark a flame. This is a fairly clever way of doing that. All that you really need is a bubbler tube down into the tank. And the way this system works is based on fluid statics. If you know the equation, pressure equals rho GH, or essentially that the pressure at the bottom of the fluid is largest, it's larger than the pressure less shallow in the fluid. That's what's being done here. So there's an air pump, and this air pump is not like an air compressor that's putting out a large volume of flow. It's just putting out a very small volume of flow. And you set the air bleed valve at the top in order to get just bubbles coming out, about 1 per second or so when the tank is full. What happens is, as the level in the tank drops, the pressure at the bottom of the tube goes down. And so the flow coming out of the air pump now prefers, instead of just all leaking through the bleed valve and just a small amount of it going through the liquid, rather more of that air will go through the liquid, because if you think about it, the air splits off out of that air pump T. Some of it goes up, some of it goes down. It's going to take whatever the path of least resistance is. And so as the resistance decreases to go through the bubble tube and down through the liquid and back out, more is going to go that way. And effectively what ends up happening is the pressure between the air pump and the bottom of the tank tube decreases, and that pressure can be sensed. So you see a little indicating transmitter there on the left that's measuring the pressure at that bubble tube, or in the bubble tube, and transmitting it. There's also a purge valve here. If you open that up, what you're doing is allowing the normal operation of the system, but if you close it, that'll force all of the air down through the bubble tube and purge it out. If any liquid ends up in the tube, it can throw off the reading, and so it's important to occasionally purge the tube in order to take a proper measurement. Now, the density of the fluid makes a difference in the reading, because from fluid statics, the density of the fluid rho is in the equation for relating the pressure at the bottom of the liquid to the height of that liquid column. And so there's another method that can be used for measuring the level in fluids if you have two or dual bubbler tubes. Now you notice there's an air supply off to the right that is pushing air through both of these tubes. There would be similar setups of bleed valves and purge valves for each of these, but let's concentrate on the bubbler tubes for the moment. The ends of the bubbler tubes are at a known height difference in the fluid. And if you measure the pressure difference between those two tubes, you can actually, and of course knowing the height difference between those two, you can actually back calculate the density of the fluid. Now either or both of the tubes can also be used for measuring the pressure in the tube, and that way measuring the height of the fluid tank. But if all you want is density, then this is one way to get it. If what you want is to compensate for density, because density can make a big difference, and throw your height readings off, because understand you're back calculating your height readings from a pressure, well then this is a way to get a measure of density in addition to a measure of pressure difference for more accurate calculations of height. There are other methods for measuring pressure differences. You'll see on the left a dry leg, and on the right hand side a wet leg measuring scheme. The LT is a level transmitter, and what that means is it takes the level measurement and transmits it to a controller. And what you'll notice is that the leg on the left side goes from the area above the liquid that says maximum level. Okay, that area, really the maximum level is that line at the top, and the tubing there attaches to the gas above the liquid. And basically that gas, having such a lower density than the liquid, ends up putting essentially the pressure at the top on the right side of LT, and the pressure on the left side of LT is the pressure of the liquid, and that difference in pressure can then be used to infer the height of the liquid column. Now if liquid does condense, if it evaporates and condenses in the leg, then it will run down and needs to not be in that right leg. The right leg needs to be dry, and so what has to happen there is the liquid goes over and down to the condensing pot. There's another, and that way it can be removed and either put back into the tank or discarded. There's another type called the wet leg, where vapor distorts the reading, but we won't go into that one for now. If you have a liquid where the liquid can form a cloud, a vapor cloud in the tank, an ultrasonic method of measuring level in the tank is not adequate, and radar has to be used instead, because radar can pierce the clouds and bounce off the more dense liquid surface. This is a lot like a radar gun in a police car. Of course, police cars these days use laser more often than radar, and essentially the idea is that the amount of time it takes for the radar signal to bounce back will be longer if the level in the tank is lower. And ultrasonic sensors work the same way. It's just measuring the transit time of a sound signal instead of a radar signal. Capacitors can be used, or essentially capacitance level sensors can be used, where you set up the tank to form actually a very large capacitor, not necessarily a very high capacitance, but a very large capacitor. And the way this works is that the liquid acts as a dielectric in the capacitor, and as that liquid level drops or rises, it changes the effective dielectric constant of the capacitor. And so by measuring that variation in capacitor across the probe and tank, you can then infer the liquid level in the tank. Now, if the fluid is conductive, you have to insulate the capacitive sensor. If it's not conductive, like gasolines and oils and things like that, then you can use a little bit cheaper capacitance level sensor that doesn't have insulation. There's no need for it in that case. But in both cases, you're measuring a capacitance change in order to infer the level in the tank. Another type of sensor is the nuclear level sensor. You might look at this and say, well, that seems scary because it has the word nuclear in it. Actually, if you have an old smoke detector in your house, you use a nuclear sensor. You have a nuclear source that's giving off radiation, and smoke causes the detection of that radiation to vary. So you use this all the time. The question is, how powerful is the nuclear source? We're being bombarded by nuclear radiation all the time, and yet we live just fine with it. To understand this, let me give you an analogy. Say you have a gallon of milk and you want to measure the level in that gallon of milk. Now, gallons of milk milk is usually put into gallons that are made of some white, high-density polyethylene. You can't really see through it. It's not clear. But imagine taking a gallon of milk and you really can't see how much milk is in it, and you put a flashlight on one side and look at the other side to see how much light makes it through. You can imagine that the liquid is going to absorb a lot of the light and it won't make it through, and you can see a very clearly marked level. That's the idea here. And so in the first image on the left, a point source of radiation is being used, and there's just a high and low detector. If all we really care about is not so much the actual level in the tank, but whether it's high or low, then this is an on-off type of sensor that would work fine. And just think of this as a flashlight, okay, where you're detecting how much light makes it. If a lot of light makes it through to the top detector, then there must not be liquid in the way, right? But if a lot of light makes it through to the bottom detector, there must not be liquid there either, right? And so that would indicate a fairly low level. Now, there are also strip sources of radiation that is kind of like taking a flashlight beam and just spreading it out, so it comes from a whole line of points. And then a strip detector. Now, this is used for measuring varying levels in the tank. And of course, the more light that's sensed, the lower the liquid level must be, and therefore the lower the level in the tank. Now, unfortunately, sensors that bounce signals off the surfaces of solids aren't as effective in tanks as they are in fluid tanks where there's a liquid, because in a fluid tank, gravity will make the level be pretty much uniform. But for solids being stored in say a silo, like a corn silo, or maybe coal or gravel, it's pretty easy for there to be an uneven level. And so sensors that bounce signals off of one point may not be the best for measuring the level in the tank. In that case, measuring the weight of the tank and its contents may be the best way to go. And so a load sensor or a load cell that's appropriate for the load expected in the tank can be used instead in order to figure out how much stuff is in the tank. Now let's turn our attention to controlling things rather than just measuring them. Valves are a very common control element, especially in any fluid process systems. And here's two very simple valves. These are both solenoid type valves. They're actually made by a company called ASCO, and they're called Red Hat valves, I guess, because of the little plastic piece at the top. But essentially, it is a solenoid that is, at the top, that's the green thing, that is interfaced with a valve body at the bottom, those goldish brass items. Now, the solenoid can be moved in or out and therefore control flow through the valve by electrical signals being transmitted to the electromagnet, basically the solenoid, to turn it on or off. Now, an interesting thing about that is that in the past, these have only been used for on-off control. But ASCO came out with a product about the time I was working for Amatrol, which has been, oh goodness, that was 2007, I guess, was the last time I was there. And they came out with these valves a few years before I left, so probably 2004-05 range, something like that. And rather than the valves being completely on or off with the spool being moved completely to either position, they applied a varying signal, a varying electrical signal, to the solenoid itself in order to float the spool. And so the spool could control the valve and move the valve stem in and out to any position desired. It was a relatively inexpensive and pretty clever little control device. Now here's a picture of solenoid valves being used to control gas flow to some burners. So here all you'd really need is on-off control. Other control valves are valves that are ball valves, and it's pretty common to have hand-operated ball valves. There's also electrically operated ball valves. And the way they work, you can see the cross-section on the right. It's pretty simple. They're called a ball valve because there's essentially a sphere with a hole in it. And when you turn the handle 90 degrees to the flow through the valve, well then the ball turns with the handle and blocks flow. But of course, if you open it up where the handle's in line with the valve, well then the flow area inside of the ball looks pretty much like the flow area in the regular segment of pipe. And so these are very low restriction valves, which is a huge advantage. One of the disadvantages of these, you might think that you could partially turn it on. It's very difficult with a ball valve to get an exact flow rate through it, because as soon as you just start opening, even 5% or so, you get pretty much full flow through the ball valve. Now, to overcome that, other valves have been developed where rather than having just a straight hole going through them, they have a variable opening. And this, imagine the sphere turning and exposing a very small area and then opening up to larger and larger area to allow more and more flow. So these are much better proportioning valves rather than just on, out, off, as the typical ball valve with a hole straight through it is good for. Now, another type of valve that can actually be quite difficult to learn about, but that is very commonly used, is a control valve with a diaphragm actuator. Now, there are some differences in the valve itself, but this is just a different way of moving the stem in and out in order to control the valve. A cutaway will help you understand. On the right is the pneumatic actuator, and on the left is the valve body. Of course, the actuator would be bolted to the top of the valve, and the yoke, of course, would be bolted to the body of the valve. That's the outside piece there. And then there's a stem there that can be moved up and down that's connected directly to the stem of the valve to pull the stem of the valve or push it in or out of the valve and control flow. The way this thing works, there's actually a diaphragm at the top, and it's sealed. The upper chamber is sealed from the lower chamber by the diaphragm, and you see the air connection at the top. When you increase the pressure on that in the air connection, what that does is that pushes the diaphragm down against a spring. And so you see that spring there, partially in cross-section. The bottom end of that spring is grounded, in other words, connected to the yoke and does not move relative to the yoke, but the upper end of the spring moves with the diaphragm. Of course, the spring is pushing up, trying to resist the diaphragm, but as you add air pressure, it pushes the diaphragm farther and farther and compresses the spring, driving the stem of the valve into the valve body. Now, these valves can be a pain to deal with, but once you get them set up, they're very reliable and very, very good devices. One of the difficulties, if you look at the stem in the valve on the left-hand side for moving the plug in and out, that stem goes into the valve body, into the flow area, and so somehow you have to prevent the liquid or gas or whatever it is from leaking out through the stem, and so it requires something called packing. So you see in this case there's spring-loaded PTFE, which is Teflon V-ring packing. Now this packing has to be pushed in fairly tight, and so it provides a lot of friction against the stem. Now of course they've used Teflon in order to minimize that friction and yet provide a good seal. But there is still significant friction, so you end up with a lot of hysteresis in this type of setup, where if you're trying to have the diaphragm actuator change direction, say you're opening the valve by pulling the plug out to allow more flow and you change directions, well, you may still be at essentially the same pressure, but you have to overcome friction going the opposite direction, because now you have static friction to overcome, and so you have to increase the pressure beyond where you were to get a different valve setting. So there's typically a lot of hysteresis in this type of device. You have to somehow overcome that. Now there are also forward and reverse acting actuators. The one on the left is the one we've been looking at so far, with air coming in the top and the bottom of the spring grounded. This is direct acting because as you increase the pressure on top of the diaphragm, the stem of the valve is pushed farther into the valve body. Both of these are considered forward motions or increasing, and so this is direct acting. Reverse acting, on the other hand, on the right-hand side, you'll notice that the air inlet has been plugged at the very top of the valve. Rather, pressure is introduced on the underside of the diaphragm, and you'll notice that the spring is in an opposite configuration, where now the top of the spring in this right-hand diagram is grounded to the yoke or the frame of this actuator, and the bottom end of the spring moves up and down. Now the air comes in, the connection is a little difficult to see, but if you look On the left-hand side of that right diagram, you'll see a small black area that sort of like an L shape. That's where the air would come into and under the diaphragm in order to modulate the diaphragm position. Now, another problem is that there's a difference between the setting when you've got the valve out of the process and when it's in the process and fluid is actually flowing through it. If you think about the fluid flow going through the valve, there's a significant restriction around the plug, right? And so the fluid is going to apply a force to the plug, and so the amount of pressure required to get a particular valve position will be different than if the fluid is not flowing. And so there's something called a bench setting, where essentially the valve is not in the process and you apply pressure to the diaphragm and, in order to get varying positions of the valve body. And the response of valve opening versus air pressure is different than when you have the valve in the process and fluid is flowing through the valve. And so in service, the response of the valve will be a little bit different. So one more thing about valves before we move on. There's a couple of different considerations. You've seen only a small fraction of the different types of valves that are available. One thing to note about valves is that it's really important to choose the right valve for the right application. There's a bunch of considerations. Cost is always number one. If you can't afford it, you can't buy it, right? So cost is certainly a consideration, but the temperature range that the valve has to operate in is very, very important. The chemical compatibility between the fluid flowing through the valve and the valve body, what it's made out of, is another huge consideration. Obviously, what's called the flow coefficient, or how much flow you expect through it. I mean, the valve for a 1 gallon per minute flow is going to be vastly different than a valve for 1,000 gallons per minute flow, right? This is a huge difference in the amount of flow that's expected. Another thing to consider is what's called valve authority. There's a mistake that I hope you won't make. I'm going to tell you about it now. There was a time I saw a system, and there were some engineers in the company I was working for that were working on this valve, and they were having a lot of trouble with it because they had 1-inch piping and they had selected a 1-inch valve to go with it. Just the so-called line size of the valve. And what that means is they just chose a valve that had threaded connections the same size as the piping. They put it in and they were having trouble with it because it turned out that for the valve to restrict flow at all, the valve had to almost completely shut off the flow. So it was at its almost the limit of its travel. And the problem with that is that the flow was very sensitive to any motion in the valve stem. And so what would happen is the valve, in trying to control the flow and modulate the flow, it would make a small change, and that would make a drastic change in the flow rate through the valve. See, valves have to have what's called valve authority. They have to be they have to be one of the main restrictions in the flow piping. Otherwise, they just don't operate very well. Well, I saw this, and I said, okay, I know how to fix this problem. I just removed that 1-inch valve, and I bought a valve that was 2 pipe sizes down. I bought a 1/2-inch valve, reduced it down on either end, put it in the line, and it worked great. Mainly because that valve was the primary restriction for flow in the whole piping system we had. And so at 90% open, the valve would change the flow, but not drastically. And at 10%, of course, it almost cut off flow, but not completely. And so we ended up solving the problem of the modulating valve by eliminating line sizing of the valve. So the amount of flow, the characteristics of the fluid flowing through the valve body are critical. Obviously, if you have a fluid that is abrasive, you need different materials for the valve body. But those are several things to consider when it comes to selecting a valve. I mentioned that these valves typically use air pressure for operation, and the typical range of air pressure used in industrial control valves is about from 3 to 15 psi. The valve diaphragms are usually large enough that's a significant difference in the amount of force to activate the valve. So that's a fairly common pressure range, but typically we control these processes with electronics, and so you typically use a current signal, and the standard for current signals is 4 to 20 milliamps. And so it's important that 4 milliamps correspond to about 3 psi and 20 milliamps correspond to 15 psi, or that the ranges of the current correspond to the range of pressure and therefore the range of motion of the valve. So what this device does is it brings in the current signal, takes in air pressure from whatever air source you have in the plant, and produces a pressure signal proportional to the current signal. Looking carefully at it, you'll notice that there are 2 different holes that are covered by, it looks like some type of rubber or something, and they're labeled zero and span. What are these two things? Well, look at the figure, and you'll notice that the light blue line looks right. You know what I mean? And at 4 milliamps, the corresponding pressure is 3 psi. At 20 milliamps, the upper end of that blue curve, the pressure is 15 psi. And this looks good. This is what you would want your current to pressure transducer to do, right? That's how you'd want it to work. Maybe the green line is the actual response. How would you change it? How would you correct it? Well, the problem is that it takes 6 milliamps to produce 3 psi, and when we give the I to P, or the current to pressure transducer, 18 milliamps, it produces 15 psi. Well, there is a range, or a slope error, or a span error, and a zero error. The entire curve needs to be shifted so that the green actual curve, the performance curve, needs to be moved to the blue ideal curve. So the first thing to do when you're calibrating this sort of thing, the first thing to do is always to adjust the zero first and then the span. The span does affect the zero, but obviously not to the extent that the zero does. So the first thing to do to get that green line to lie on top of the blue line is to adjust the zero, bring the whole curve down, and then increase the span or increase the range. After you do that, it's important to go back and check the 0 point again. Now, valves have hysteresis, current to pressure transducers have hysteresis, most things do, and all that really means is that the input-output characteristics depend on whether the input is moving upscale or downscale. The output will be different depending on whether the input is increasing or decreasing. So in the case of a valve, as the pressure increases, pushing the stem farther into the valve, you'll get a different flow than when the pressure is being released and backed off, going downscale, and pulling or allowing the stem to come back out of the valve. You'll get different flow rates even though you might be at the exact same pressure. That is hysteresis. In current to pressure transducers, the amount of pressure you get for a given current signal will depend on whether the input current is increasing or decreasing. And so measuring the hysteresis is also very important.